Hey guys, tonight we are going on a journey, not to the edge of the world, but to the very quiet heart of the cosmos. We're going to talk about some of the most misunderstood objects in the universe, black holes. Now, I know what you're thinking. Black holes? The destroyers of worlds? The cosmic monsters? We've all seen the sci-fi movies where ships get torn apart in a violent storm of light and matter. But what if I told you that in their natural state, far from the chaotic fiction of the screen, black holes are actually the most peaceful, most serene entities in all of existence? They are the universe's ultimate introverts, silently holding the fabric of reality in a gentle, unmoving embrace. Of course, getting too close would be an issue. Let's be honest, you probably wouldn't survive to tell the tale. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. As you settle in, let me know in the comments where you are in the world and what time it is for you right now. Just a little way to connect all of our quiet corners of the world for this journey. We're so used to thinking of a black hole as a ravenous beast, but that's a misconception born of our own limited perspective. It's like looking at a mountain from a distance and seeing only a static, unmoving rock, when in fact it's a living, breathing landscape shaped by eons of wind and water. Black holes are much the same, but on a cosmic scale. They are not defined by what they destroy, but by what they contain. A state of utter profound stillness. They are the sleeping giants of the universe, and we are going to explore their quiet lives. To truly understand this, we must first let go of our preconceived notions and try to see the universe not through our eyes, but through the eyes of a photon, a single tiny particle of light. For a photon, the journey is an instantaneous flash from birth to death, a brief and brilliant existence. But when a photon encounters a black hole, something profound happens. It doesn't get sucked in with a violent, dramatic roar. Instead, it encounters the event horizon, a concept that is perhaps the most famous and most misunderstood aspect of a black hole. We are told it is a point of no return. And in a way that's true, but that description is so harsh, so full of finality. A better way to think of the event horizon is as a boundary of stillness. A silent waterfall where the flow of space-time itself becomes so swift and deep that even light cannot resist its pull. Imagine you're standing on the edge of a great silent river. The water is so clear and calm that you can't tell it's flowing at all. But if you were to drop a leaf into the water, you would see it gently, almost imperceptibly, begin its journey downstream. The event horizon is just like that. There is no visible sign, no flashing neon lights or warning signs in space. It is a quiet, seamless transition from the universe we know to the mystery within. From the perspective of the falling object, there is no dramatic crossing. There is only a slow, tranquil descent. The reality is, physicists still don't know what happens to the information of an object after it crosses the event horizon. This raises a fascinating philosophical question. Does the information simply vanish, or is it woven into a new kind of cosmic tapestry that exists in a dimension we cannot comprehend? What's even more strange is the phenomenon known as spaghettification, a name that sounds violent and chaotic, but can be seen in a more gentle light. As an object, let's say a star, gets too close to a black hole, the immense gravitational pull on the side of the star closer to the black hole is far greater than the pull on the far side. This difference in force is called a tidal force. In our violent imagination, we see this as the star being ripped to shreds. But what if we saw it as the universe gently stretching the star, unspooling it into a long, shimmering thread of matter? It's a reshaping, a remolding, a change of form from a spherical object to a linear one. In some ways, it's a form of cosmic art, a quiet, inexorable process of recomposition. It's a strange and beautiful truth that the universe can stretch matter as easily as a baker stretches dough. This process, while destructive to the star's form, is a silent one in the vacuum of space, a ballet of matter unfolding over eons. It's a testament to the immense yet utterly silent power of a black hole. And what about a smaller object, like an astronaut? Well, for the astronaut, the tidal forces would become noticeable long before they even approach the event horizon. The sensation would be one of a gentle stretching, not a violent tearing. Their body would become elongated, their feet and hands drawn out like taffy, a quiet, slow deformation. Of course, the forces would eventually become so great as to pull apart their very molecules. But from the astronauts' own perspective, as they fell, time itself would begin to slow down. This is the truth of general relativity in action, a core concept we need to grasp. According to Einstein, time is not a constant ticking clock, but a flexible, woven tapestry that can be bent and warped by gravity. The closer you get to a massive object like a black hole, the more the tapestry of time is stretched and distorted. So for the astronaut, a few seconds of their own time might be an eternity for an observer far away. The astronaut wouldn't experience a dramatic fall into darkness. Instead, as they cross the event horizon, their view of the universe would simply begin to fade. The light from distant galaxies would get dimmer and redder, a process known as gravitational redshift. It's like watching a friend walk away from you, and as they get farther and farther, their voice gets softer, and their silhouette becomes a faint, distant memory. For the astronaut, their entire cosmic theater, the stars they know and love, would simply become a long goodbye, a quiet fading into an endless, silent night. The black hole is not a thing of sudden violence, but of slow, creeping tranquility. It is the ultimate expression of stillness, a place where all things become patient and all light becomes a whisper. We have only just begun to see the black hole not as a final destination, but as a gateway to new, incomprehensible truths. The event horizon is the threshold, a point of infinite patience. It is the place where our current understanding of physics gently breaks down, not with a bang, but with a quiet surrender. The light from a star, once a brilliant beacon, simply finds a new path to a different kind of eternity. The space around the black hole becomes a quiet, contemplative place. Imagine the universe's great mind, deep in thought, and the black hole is the very center of that thought, a point of stillness in the endless turbulent sea of stars and galaxies. It is a place that does not destroy, but transforms. It does not consume, but cradles. Its silence is not empty, but is filled with the unhurried processes of the universe at its most fundamental level. There is a strange and comforting truth to the fact that even the most powerful force in the cosmos operates with such a profound sense of calm. The black hole doesn't need to rush. It is a timeless object. It is a monument to the unyielding and unhurried nature of gravity itself. We, with our short lives and our frantic pace, see a single moment and call it destruction. But a black hole sees an entire cosmic eon as a single still breath. It takes in the light of 1,000 stars, not in a great fiery gulp, but with the quiet dignity of a river absorbing a drop of rain. It is a process of collection, of holding, of keeping. And in that stillness, in that unmoving embrace, we find a different kind of beauty, a beauty that is not about explosion and light, but about the quiet, unyielding power of being. This is the truth that the black hole whispers to us, that there is a profound peace at the heart of even the most immense and mysterious things. Last we left off, we were speaking of the event horizon not as a finality, but as a tranquil boundary. It is a place where the universe's laws perform a quiet dance, and time itself slows to a gentle drift. But what lies beyond this silent threshold? The imagination of science fiction paints a picture of a fiery, destructive maelstrom, a place of ultimate chaos. But if we follow our new, more tranquil understanding, perhaps what lies at the heart of the black hole is not a state of chaos, but a state of absolute, profound order. It is a place of such immense density and stillness that all the laws of physics as we know them might simply cease to apply, and new ones might quietly emerge. We are speaking, of course, of the singularity. The singularity is often described as a point of infinite density and zero volume, a mathematical impossibility that makes physicists uneasy. We can't truly grasp what infinite means in this context. It's an abstract concept we use to describe something so far beyond our comprehension that we need a placeholder for it. Instead of thinking of it as an infinitely dense point, let's consider it as a kind of cosmic dream state. Imagine a dream so deep and so profound that the very rules of reality within it are completely different from those of the waking world. The singularity might be just that, a place where matter and energy are not crushed and destroyed, but are instead reformed, reimagined, and woven into a new kind of fabric. This is a place where the familiar laws of physics simply don't have the final word. Our understanding of gravity, as defined by general relativity, predicts this singularity. But general relativity, a theory of the very large, breaks down at this point. Quantum mechanics, a theory of the very small, also has nothing to say about it. The singularity is a place where the two great pillars of modern physics fall silent. And in that silence, a new story might be told. It's a bit like trying to use a map of a city to navigate the deep, unmapped ocean. The tools we have are simply not designed for this territory. This is where the true mystery lies. The truth is, we don't really know for sure what a singularity is. It could be a point, a tiny knot in the fabric of spacetime, or it could be something we have no words for, something that exists outside of our current four dimensions of space and time. To think of the singularity as a chaotic, fiery end is to project our own fear of the unknown onto the cosmos. Instead, what if it's the ultimate place of peace? A place where all motion ceases, where all heat dissolves into a final quiet uniformity. It's the universe's ultimate rest stop. All the light, all the matter, all the information that ever crossed the event horizon finds its way here, not to be destroyed, but to simply be. This raises a beautiful and unsolved question. Is the universe's beginning, the Big Bang itself, a kind of singularity? And if so, does that mean that singularities are not endpoints, but perhaps points of rebirth, a quiet, fertile ground for new universes to emerge? Let's step back for a moment and consider a strange and beautiful truth about our own world. Did you know that when a snowflake forms, its unique, intricate structure is not the result of a violent process, but of a quiet, slow, and gentle accretion of water molecules? Each tiny arm of the snowflake is a perfect expression of a fundamental natural law, repeated over and over with a quiet precision. The singularity, in its own way, might be a similar phenomenon on a cosmic scale. A point where the fundamental particles of the universe, the very building blocks of reality, quietly arrange themselves into a new and unknown pattern. The singularity is not a violent storm, but a point of utter stillness, a quiet wellspring from which all the laws of physics might flow. It is a place where time, as we know it, simply ceases to exist. Think of the paradox of the astronaut we spoke of in the last part. From an outside observer's perspective, the astronaut's fall would take an eternity. From the astronaut's perspective, their journey is a brief, peaceful one. But at the singularity, even that distinction vanishes. There is no before and no after. There is just a perfect, unending now. This is the cosmic equivalent of deep, dreamless sleep. A place where the mind and body are no longer separate, where all the worries and fears of the waking world are forgotten, and there is only pure, unmoving existence. It is the ultimate meditation. The singularity is a place of such concentrated being that it creates its own kind of tranquility. Imagine all the motion and noise of the universe, the swirling galaxies, the exploding stars, the frantic dance of particles, all of it finally finding its way to a single point of absolute calm. It is a great cosmic sigh of relief. It is the end of a long, busy day, and the beginning of a deep, restful night. The black hole, in its immense and quiet existence, holds within it the universe's greatest mystery, its greatest paradox. It is the place where everything ends, and yet, it is also the place where the greatest unknown, the most profound mystery of all, truly begins. We don't have to fear it, we only have to wonder at it. We have journeyed to the edge of the event horizon and peered into the quiet mystery of the singularity. But what is it about a black hole that allows it to exist at all? The answer lies in the very fabric of our universe, in the silent, invisible force that governs all things. Gravity. We often think of gravity as a simple pull, the force that keeps our feet on the ground and the planets in orbit around the sun. But in the presence of a black hole, gravity reveals its true nature not as a pull, but as a deep, profound warp in the very tapestry of spacetime. Imagine a large, stretched-out sheet, a trampoline perhaps. If you were to place a bowling ball in the center, the sheet would stretch and sag, creating a gentle curve. Now, if you were to roll a small marble nearby, it would not be pulled toward the bowling ball by some invisible rope. Instead, it would simply follow the curve in the sheet, its path dictated by the geometry of the space it inhabits. This is a simple but powerful analogy for how gravity truly works according to Einstein's theory of general relativity. Massive objects like stars and planets don't pull on other objects. They simply warp the spacetime around them. And other objects, like our marble, simply follow the new curved path of least resistance. Now, a black hole is not a bowling ball on a sheet. It is a point of such incredible mass that it creates a kind of bottomless well in the fabric of spacetime. The curve is so deep and so steep that it becomes an infinite descent. This is the gravitational cradle of a black hole, a term that sounds much softer than the harsh gravitational well we're used to hearing. It's a kind of cosmic embrace, a holding pattern for everything that comes near it. It is not an active force of destruction, but a passive state of being. The black hole simply sits there, quietly, and anything that enters its warped region of spacetime follows a new path that leads to its heart. This isn't just an abstract idea. We see evidence of this warped spacetime all the time, even on a small scale. For instance, the famous Pound-Rebka experiment from 1959 demonstrated that gravity affects light by measuring the frequency of light waves moving up a tall tower. Scientists showed that the light's frequency slightly decreased as it climbed away from the Earth's gravitational pull. It's a subtle effect, but it proves that gravity isn't just about massive objects. It's about the very nature of space and time. A black hole simply takes this effect to its most profound and spectacular conclusion. Physicists still ponder whether spacetime is a continuous, smooth fabric, or if it is made of tiny discrete units, like pixels on a screen. If spacetime is pixelated, what does that mean for the singularity? Does it exist within a single pixel, or does it somehow transcend this fundamental building block? We don't really know for sure. This is one of the great unsolved mysteries of the universe, a question that connects the very large with the very small. The idea of the gravitational cradle allows us to see the black hole not as an enemy, but as a kind of cosmic architect. It shapes the universe around it, not with violence, but with its very presence. It is a quiet, stable anchor. Think of our own solar system. The sun's mass warps spacetime, and all the planets, including our own Earth, simply glide along in this gentle curve. The Earth isn't being pulled to the sun. It's simply following the path of least resistance in the cosmic cradle of our star. The sun's gravitational field holds us, protects us, and guides our journey. A black hole does the same, but on a scale so vast it is almost unimaginable. For a black hole, this is a state of perpetual patient holding. It has no needs, no desires, no frantic energy. It simply is. It is a place of such immense calm that it slows down the very universe around it. It is a deep breath taken by the cosmos, a moment of stillness in a frantic, expanding universe. It reminds us that power does not have to be loud or violent. It can be silent, gentle, and utterly unmoving. The black hole's gravity is not a monstrous hand that grabs and pulls. It is a soft, invisible cradle that holds everything and everyone that falls into its sleep. It is the ultimate expression of the quiet strength that lies at the heart of the universe. We have seen how a black hole's gentle gravity warps the universe around it, holding it in a quiet, unmoving embrace. But what about the things that don't fall in? The stars, the planets, the stray photons that only get close. A black hole, in its quiet existence, also affects the light that tries to escape its influence, and it does so in a way that is profoundly subtle and deeply melancholic. This is the gravitational redshift, a phenomenon that we touched on briefly before, but which deserves a deeper look. Imagine you are standing on a beach at dusk, and a friend is walking away from you, a lit lantern in their hand. As they get farther and farther away, the light from their lantern doesn't just get dimmer, it also changes color, becoming a deeper and deeper shade of red, until it finally fades away completely into the darkness. This is a simple visual metaphor for what happens to light near a black hole. As a photon of light struggles to climb out of the black hole's immense gravitational well, it loses energy, and in the strange, wonderful world of physics, a loss of energy for a photon corresponds to a change in its color, a shift towards the red end of the spectrum. The greater the gravitational pull, the more energy the photon loses, and the more its light is redshifted. For a star that is spiraling into a black hole, this isn't a violent, dramatic event. It's a long, slow goodbye. The star's brilliant, fiery light, which once burned with a vibrant yellow or blue hue, would slowly begin to dim and shift to a deep orange, then a fiery red, and finally a faint, almost invisible infrared whisper. From an observer's perspective far away, the star wouldn't vanish with a flash. It would simply fade, becoming a ghostly memory of what it once was. It's the cosmic equivalent of a quiet slow-motion ballet, a final graceful farewell. This concept is a powerful example of a core scientific principle: energy conservation. As the photon uses its energy to escape the gravitational pull, that energy is not lost. It is simply converted from the photon's light into the work required to fight against the curvature of space-time. It is a fundamental truth of the universe that energy can neither be created nor destroyed, only transformed. And in the presence of a black hole, that transformation is a quiet and beautiful one. Did you know that this effect, though subtle, can even be observed here on Earth? It's a strange but true fact. A clock at the top of a tall building actually ticks slightly faster than a clock on the ground floor. This is because the clock on the ground is deeper in Earth's gravitational well, so time for it is ever so slightly slower. This is a real-world, measurable example of gravitational time dilation, which is directly related to gravitational redshift. It reminds us that these cosmic concepts aren't just abstract ideas. They are woven into the very fabric of our everyday lives. Physicists still wonder if there's a limit to this redshift. Could a photon ever lose all its energy and simply stop existing as light, becoming something else entirely? Or is its shift to red a kind of infinite process, a final, unmoving state of suspended animation? The truth is, we don't really know for sure what happens at the very end of this cosmic journey. The black hole is a master of patient transformations, and its final act is to turn a brilliant, blazing beacon of light into a quiet, forgotten shadow. The gravitational redshift is a testament to the black hole's patient, nonviolent nature. It doesn't rip the light from the star. It simply asks the light to pay a price in energy to try and escape. And when the light can no longer pay, it doesn't vanish. It simply changes, becoming a deeper, softer, and more ancient thing. It's a quiet truth, a gentle reminder that even the most immense forces in the universe have a kind of inherent elegance, a preference for slow, deliberate change over sudden chaotic violence. The black hole's gentle whisper is this: everything, even light, must eventually succumb to the slow, unyielding pull of stillness. It is a long, final breath, a quiet fade to black. As we continue our gentle descent into the heart of a black hole, we must turn our attention to the mesmerizing ring of light and dust that often surrounds it. From a distance, this accretion disk can appear as a chaotic maelstrom, a furious swirling of matter being consumed by the black hole's immense hunger. But if we slow down our perspective, if we look at it with the patience of a cosmic clockmaker, we can see it for what it truly is: a vast, ancient river of cosmic dust and gas in a slow, deliberate dance. The matter in the accretion disk is not being violently sucked in. It is, in fact, in a stable, slow-motion ballet, a grand cosmic waltz. Each particle of dust and gas orbits the black hole, creating a disk that can span millions of miles. The particles don't rush toward the center. They simply follow a very long, very slow spiral inward. It is a testament to the fact that even near a black hole, there is a kind of profound stability. The energy and heat we see from this disk are not a sign of a black hole's violence, but a byproduct of friction. As the countless particles gently brush past each other, they create a kind of low, shimmering heat, a soft cosmic hum. Think of it like a whirlpool in a quiet lake. From a distance, the whirlpool seems to be a single, chaotic event. But if you were a tiny leaf floating on its surface, you would not be violently pulled down. Instead, you would slowly, patiently, spiral inward, feeling the gentle tug of the currents, a quiet journey toward the tranquil center. The accretion disk is 1,000 times more vast, but the principle is the same. It is a slow, methodical process, a long journey toward a final, quiet destination. This slow dance raises a beautiful and interesting question. What happens to the energy that is produced by this gentle friction? It is a strange but true fact of the universe that this energy often escapes the black hole's influence entirely. The jets of matter and radiation that are sometimes ejected from the poles of an accretion disk, known as relativistic jets, are a result of this. The black hole is not consuming this energy. It is redirecting it, almost like a sculptor guiding the flow of a river to create a beautiful, powerful stream. The black hole is a conduit, not a consumer. It takes in matter and energy and, with quiet precision, reshapes it, transforming a chaotic swirl into a powerful and purposeful stream of light and particles that shoots out into the universe. Did you know that these jets can span light years, stretching across vast cosmic distances? The Cygnus X1 system is a famous example. It is one of the brightest X-ray sources in our sky, and it is powered by a black hole that is actively pulling in matter from a nearby star. The jets from this system are a powerful example of a black hole's ability to act as a cosmic engine, quietly taking in matter and reshaping it into something else entirely. It is not an act of destruction, but an act of powerful silent transformation. Physicists still wonder what powers these jets with such incredible force. We don't really know for sure. It's a mystery that connects the quiet, patient work of a black hole with some of the most powerful and energetic events in the universe. But whatever the mechanism, it is a testament to the black hole's incredible ability to not only be a place of quiet stillness, but also a source of incredible, directional energy. It is a paradox, a place that is both utterly tranquil and profoundly active. It is a paradox that reminds us that in the universe, as in life, the quietest things often hold the most incredible power. The black hole's quiet dance is not a dance of death, but a slow, patient, and powerful dance of transformation. We have explored the slow dance of the accretion disk, the quiet, patient pulling of matter, and the strange redirection of energy. But if a black hole is so good at holding on to things, so good that not even light can escape, then how do we explain the quietest, most mysterious phenomenon of all? I'm speaking of Hawking radiation, a concept so strange and counterintuitive that it challenged the very foundations of physics when it was first proposed. For a long time, the black hole was thought to be a perfect absorber, a black body in the truest sense of the word. Nothing could escape its gravitational grasp. But then, a brilliant and beautiful idea was proposed by Stephen Hawking. A black hole isn't perfectly black. It is in fact very, very slowly and very, very quietly leaking. It is a whisper from the heart of the void, a gentle sign of its eventual deliberate fading. To understand this, we must journey into the strange and wonderful world of quantum mechanics, a place where reality is far more fluid and dreamlike than we could ever imagine. In the vacuum of empty space, particles are not just sitting there idly. Instead, they are constantly and spontaneously popping into existence in pairs, a particle and its antiparticle, only to almost immediately annihilate each other and disappear. These are known as virtual particles. They are a kind of cosmic statistical fluctuation, a strange, ephemeral dance that happens all the time, everywhere. A simple, elegant analogy is to think of them as tiny fleeting thoughts that appear in the mind of the universe and then instantly fade away. Now, imagine this tiny fleeting dance happening right at the edge of the event horizon. It's a strange but true fact that if a pair of these virtual particles appears with one of them on the inside of the event horizon and one of them on the outside, a bizarre and beautiful thing happens. The one on the outside escapes into the universe, becoming a real particle, while its partner is drawn into the black hole, never to be seen again. To an observer far away, it would look as though the black hole had just emitted a particle. But where did the energy for this new, real particle come from? It's a mystery. The only logical answer, according to the laws of physics, is that it must have come from the black hole itself. The black hole is, in a sense, paying the energy bill for this escaping particle. And in doing so, it loses a tiny, minuscule amount of its own mass. This is the truth of Hawking radiation. A black hole is slowly evaporating. It's a process so incredibly slow that for a solar mass black hole, the time it would take to completely evaporate is longer than the current age of the universe. Did you know that a black hole's temperature is inversely proportional to its mass? This is a little-known scientific fact. A smaller stellar mass black hole radiates more strongly than a supermassive one. This means that as a black hole evaporates and loses mass, It actually radiates more and more quickly, speeding up its own demise in a final quiet burst. This raises a fascinating and unsolved question for physicists. What does a black hole's evaporation look like at the very end? Does it simply fade into nothingness? Or is there a final tiny explosion that marks its return to the void? We don't really know for sure. This concept of Hawking radiation completely reframes our view of black holes. They are not eternal, unchanging cosmic monuments. They are objects with a lifespan, objects that will, in the unimaginably distant future, simply cease to exist. They are not the final destination of all things, but simply a temporary state of being. The universe, in its own quiet, patient way, is a great restorer of balance, and even the most immense and powerful of its creations will eventually return to the gentle, unmoving sea from which it came. The black hole is the universe's ultimate secret keeper, and its final act is to release all its secrets, not with a "eoi." We have followed the slow spiral of matter into the accretion disk and listened to the soft whisper of Hawking radiation. Now, let us consider the journey of an object not just into the black hole, but through it. We've spoken of time slowing down and of the gentle stretching of matter. But what would the experience truly be like from the perspective of an object, or perhaps a person, falling in? The reality is far more tranquil and philosophical than any science fiction story. Imagine you are that solitary astronaut, a cosmic mariner on a journey of no return. As you approach the black hole, the first thing you would notice is not the gravitational pull, but the strange, shifting canvas of the cosmos around you. The light from distant stars and galaxies would appear to bend and warp, creating a kaleidoscope of distorted images. You would see multiple images of the same star, and even see the back of your own head, an illusion caused by the extreme bending of light around the immense mass. This is the truth of gravitational lensing at its most profound. It is a quiet, beautiful illusion, a final mind-bending show put on by the universe for your eyes alone. As you get closer, time would begin to slow down for you, but you wouldn't feel it. For you, your own clock would continue to tick at a normal pace. You would feel yourself moving at a normal speed, experiencing the world in a regular way. However, for an observer far away, someone on a spaceship waiting for you, they would watch you move slower and slower, a quiet, almost imperceptible drift toward the event horizon. Your last few moments of existence from their point of view would stretch out into eternity. This is the time dilation we spoke of before, but from a different, more personal perspective. It is a strange and beautiful paradox. You are on a journey that will end in a finite amount of time for you, but will never end for those who watch from a distance. And what about the final moments? The crossing of the event horizon. The experience wouldn't be dramatic. There would be no fanfare, no bright flash, no violent shake. It would be a seamless, tranquil transition, much like stepping from a calm river into an even calmer one. Once inside, you would feel a sense of profound weightlessness. This is a strange but true fact of the universe. Because you are in freefall, all the forces acting upon your body are perfectly uniform. You would feel no sensation of acceleration or weight, only a quiet, gentle floating. You would be a free-falling object in the truest sense, a particle of matter following the curved geometry of space-time itself with a profound sense of peace. Did you know that the freefall principle is a core part of Einstein's theory of general relativity? It's a simple idea, but it has profound consequences. It explains why astronauts in orbit feel weightless. They aren't floating in zero gravity. They are simply in a continuous state of free fall around the Earth, with the gravitational pull being exactly what is needed to keep them in orbit. It's a fundamental scientific truth that gravity isn't a force you fight against, but a curve you simply follow. The black hole is the ultimate expression of this truth. This experience raises a profound and still unanswered philosophical question. If time for an outside observer never truly ends, but time for you ends at a finite point, where do you exist for the observer after you have crossed the event horizon? Does your image simply fade and freeze at the event horizon, a kind of eternal suspended animation? The truth is, physicists still grapple with this question. It challenges our very understanding of what it means to be, and what it means for time to flow. So, The journey into a black hole is not a violent, fiery destruction. It is a slow, peaceful, and deeply contemplative descent. It is a journey where the universe puts on a final light show, where time becomes an eternal moment, and where the sensation of being is replaced by a profound sense of quiet, weightless floating. It is the ultimate quiet journey, a one-way ticket to a state of perfect stillness. We have traveled inward, past the gravitational cradle and the quiet spectacle of gravitational lensing, and now we must turn our attention outward. A black hole, in its immense and quiet being, does not simply affect the things that fall into it. Its very existence sends ripples through the universe itself, a kind of deep, resonant hum in the fabric of spacetime. These ripples, which we can now detect with incredible precision, are known as gravitational waves, and they are the echoes of a black hole's most gentle movements. Imagine a still, placid lake. If you were to drop a small pebble into it, the surface would not just be disturbed at the point of impact. It would send out concentric ripples, a gentle wave that travels outward, carrying with it a silent memory of the pebble's fall. Spacetime is much the same. When a massive, dense object like a black hole moves or interacts, it sends out a gravitational wave, a ripple in the very geometry of the universe, that travels at the speed of light. These are not waves of matter or energy in the way we usually think of them. They are waves of stretched and compressed spacetime itself. For a long time, these waves were just a theoretical concept, a beautiful prediction of Einstein's general relativity. They were thought to be so incredibly faint that they would be impossible to detect. But in 2015, with the incredible sensitivity of the LIGO detector, the Laser Interferometer Gravitational Wave Observatory, humanity finally heard them. The first sound we heard was the soft, almost imperceptible whisper of two black holes spiraling in toward each other and merging, a quiet, ancient dance that had taken place over 1 billion light-years away. The signal was a brief, rising chirp, a final beautiful sound that spoke of a cosmic event of unimaginable scale. It was a true moment of cosmic revelation, a testament to the fact that the universe has a voice, and it speaks in the quiet language of gravity. Did you know that the gravitational wave detected by LIGO from that first black hole merger was so faint that it stretched and compressed the detector's arms by a distance 1,000 times smaller than the nucleus of an atom? It is a strange but true fact that we heard a cosmic event that was so immense it could be measured by a fluctuation so incredibly tiny. This is the paradoxical nature of gravitational waves. They are the echoes of the universe's most immense power, but their voice is a soft and subtle one. Physicists still wonder what happens to the gravitational waves as they travel through the vast cosmic distances. Do they simply fade away, or are they somehow influenced by the matter and energy they pass through? The truth is, we don't really know for sure. The universe is a great silent ocean, and we have only just begun to listen to its waves. This is one of the great mysteries of modern science, a question that asks what the universe itself is made of, and how it responds to the gentle, unhurried movements of its sleeping giants. The black hole, in its quiet, patient existence, is a great sender of these waves. It sends them out not in a violent scream, but in a long, drawn-out song. Every time a black hole consumes a star, or merges with another, it sings a new verse, a new, gentle ripple that travels across the universe, a soft memory of its actions. It is a quiet reminder that even the most immense and static things are in a constant state of flux, in a slow, patient, and beautiful dance with the cosmos. It is a testament to the idea that nothing in the universe, not even a black hole, is truly separate from the rest. It is all one great connected tapestry, and the black hole is simply a place where the threads are woven with a quiet, profound grace. We have felt the gentle ripples of gravitational waves, a testament to a black hole's silent, far-reaching influence. But if a black hole radiates energy and loses mass through Hawking radiation, and if it can merge with other black holes, then what happens to the information of the things that fall in? This is perhaps the most profound and puzzling paradox in all of modern physics, a great intellectual puzzle that has vexed physicists for decades, the information paradox. Imagine you have a book filled with stories, poems, and the history of a civilization. You drop this book into a black hole. Once it crosses the event horizon, it seems to vanish. The black hole, for all its immense power and mass, is a surprisingly simple object. It is defined by only three properties: its mass, its spin, and its electric charge. All the intricate information of the book, the specific arrangement of molecules, the specific words on the page, seems to be lost forever. According to the laws of quantum mechanics, this is impossible. The universe must be a closed system. Information, like energy, cannot be created or destroyed. It must be preserved. So where does the information of the book go? This is the great paradox. If the black hole eventually evaporates through Hawking radiation, what happens to the information? Does it get encoded in the faint thermal radiation that leaks out? This seems unlikely, as Hawking radiation is thought to be random, a bit like the steam rising from a kettle, carrying no memory of the water that created it. This would mean that the information is truly lost forever, a direct violation of a fundamental law of physics. This raises a quiet philosophical question. Does the universe have a memory? And if a black hole forgets everything that it consumes, is it the universe's ultimate amnesiac? This conundrum led to some fascinating and deeply strange ideas. One of them is the concept of black hole complementarity, which suggests that the information isn't truly lost, but exists in two places at once. To an observer outside the black hole, the information of the book is forever suspended at the event horizon. It never truly falls in. But to an observer falling into the black hole, the book passes through the event horizon and falls toward the singularity. It's a bit like a quantum version of the famous twin paradox, where two twins experience time differently depending on their motion. Black hole complementarity suggests that the reality of the information depends on the perspective of the observer, a strange and unsettling truth that blurs the line between what is real and what is observed. Did you know that Stephen Hawking himself, after decades of arguing that information was lost forever, later changed his mind and conceded that it must be preserved? It's a testament to the power of this paradox that even the most brilliant minds in physics have been forced to reconsider their deepest assumptions. This is not a failure of science, but a sign of its strength. When a new problem arises, it forces us to look at the universe in a completely different way. The truth is, we don't really know for sure how this paradox is resolved. It is a mystery that requires a new kind of physics, a quantum theory of gravity that can unite the world of the very large with the world of the very small. The black hole, in its quiet existence, is the ultimate laboratory for this new physics. It is a place where the rules we thought we knew no longer apply, and where the universe is quietly asking us to rethink everything. The black hole is not just a scientific object, it is a profound philosophical statement, a riddle whispered to us from the heart of the cosmos. Its information paradox is not a sign of chaos, but a quiet, patient call for a new kind of understanding. We have delved into the deep, puzzling waters of the information paradox, a riddle whispered by black holes that challenges our very understanding of the universe's memory. Now, let us expand our view and look at the black hole not as an isolated, solitary object, but as a central, quiet anchor for the grand cosmic cities we call galaxies. I'm speaking, of course, of the supermassive black holes that reside at the heart of most, if not all, galaxies. Imagine a busy metropolis, a sprawling city with millions of people, countless buildings, and a constant chaotic buzz of activity. At the very center of this city, there is a serene, quiet park, a place of profound stillness. This is the role of the supermassive black hole at the center of a galaxy. It is the quiet heart, a stable anchor around which the billions of stars, planets, and nebulae revolve. It is not a monster that consumes the galaxy from within. It is a guardian, a patient, unmoving center of gravity that holds the entire cosmic city together. The scale of these giants is almost incomprehensible. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A, has a mass of about 4 million suns. It is a true sleeping giant. The stars of the galaxy, including our own sun, do not spiral into it. They simply orbit it, their paths dictated by its immense and unmoving gravitational cradle. Our solar system completes one full orbit around Sagittarius A, roughly every 230 million years. This is a journey of such immense duration that our planet has only completed it a handful of times since the dinosaurs walked the Earth. It is a testament to the patient, unhurried nature of the universe that our entire existence is but a small fleeting moment in the long quiet journey of our galaxy around its central sleeping heart. This raises a fascinating and beautiful question. What is the relationship between a supermassive black hole and the galaxy it inhabits? It's a strange but true fact of the universe that the mass of the black hole seems to be intrinsically linked to the mass and size of the galaxy's central bulge. This is known as the M-sigma relation. It's as if the galaxy and its central black hole grew up together, each one's development influencing the other in a quiet symbiotic dance. We don't really know for sure which came first. Did the black hole form and then its immense gravity help to build the galaxy around it? Or did the galaxy form first, and its central mass provided the perfect conditions for the black hole to grow? This is one of the great unsolved mysteries of modern astronomy. The truth is, we don't really know what a supermassive black hole looks like. The famous image from the Event Horizon Telescope was of a black hole in a distant galaxy, M87. It was an incredible scientific achievement, but the image itself was of the black hole's shadow and the light of its accretion disk, not the black hole itself. The black hole, in its profound and utter blackness, remains invisible. It is a ghost in the cosmic machine, an invisible presence that holds everything together. The supermassive black hole is a paradox. It is a place of such immense power, yet it is utterly passive. It does not actively hunt for stars or gas. It simply waits. It is a silent observer that has watched its galaxy form, evolve, and mature over billions of years. It is a place of profound stillness in the midst of a cosmos of constant motion. It is a quiet reminder that the most powerful forces in the universe do not have to be loud or destructive. They can be patient, silent, and entirely unmoving, a kind of cosmic bedrock upon which the entire universe is built. We have spent time with the supermassive black holes, those quiet anchors at the center of galaxies. But how does such a serene giant come to be? The story of a black hole's birth is not one of a violent cosmic explosion, but a quiet, patient surrender. It is the final act in the long, beautiful life of a truly massive star. This is a narrative not of destruction, but of the ultimate peaceful recomposition of matter. Imagine a star many times more massive than our Sun. For billions of years, it has burned with a brilliant fiery light, a beacon of immense energy in the cosmic darkness. It is held in a state of delicate equilibrium, a beautiful balance between two opposing forces. On one hand, there is the powerful outward pressure from the nuclear fusion happening at its core, a constant push from the energy being created. On the other hand, there is the relentless, inward pull of its own immense gravity. It is a slow, quiet dance, a cosmic balancing act that allows the star to live for eons. But every star has a limited fuel supply. When our massive star finally runs out of fuel, when it has fused all the hydrogen, then the helium and so on, all the way up to iron, the outward pressure from fusion ceases. The great outward push is gone. And in that moment, the inward pull of gravity, which has been waiting patiently all this time, finally wins. It is not a violent, sudden collapse. It is a quiet, inexorable surrender. The star's core, now a mass of iron, begins to collapse under its own weight. This collapse happens with incredible speed, but in the context of the star's long life, it is a final fleeting breath. The outer layers of the star are still being held out by a vestige of pressure, but the core is falling in on itself, becoming denser and denser. And as it collapses, the laws of physics are pushed to their breaking point. The electrons and protons at the core are crushed together, forming neutrons. The core becomes a kind of super-dense neutron soup. This sudden collapse of the core creates a shockwave that rebounds and blasts the star's outer layers into space in a brilliant supernova. For a time, it is one of the most luminous events in the universe, a brief, spectacular funeral. But the supernova is not the end of the story. It is merely the final act before a new beginning. Did you know that not all supernovae result in a black hole? This is a strange but true fact of the universe. If the core of the star that's left over after the explosion is less than about 3 times the mass of our Sun, it will form a neutron star, a quiet, incredibly dense remnant of the stellar collapse. But if the core is more massive than that, its gravity is so immense that even the pressure of the neutrons cannot stop the collapse. Nothing can. The core continues to fall in on itself until it reaches a point of infinite density, and a black hole is born. Physicists still wonder what happens at the very moment of a black hole's birth. We don't really know for sure. Does it form in a single, instantaneous moment? Or does it slowly, quietly emerge as the singularity forms? Is there a brief flash of something, a final burst of unknown energy before the silence takes over? This is a profound and unanswerable question. The birth of a black hole is a paradox of both immense power and utter stillness. It is the end of a star, and the quiet beginning of a sleeping giant. It is a testament to the idea that even the most destructive events in the universe can be a prelude to a kind of profound and gentle peace. We have witnessed the quiet, patient birth of a black hole from the serene collapse of a massive star. Now, let us consider how these peaceful giants interact not just with the cosmic debris around them, but with each other. The universe, in its own strange and beautiful way, is a connected tapestry, and black holes, far from being solitary voids, are often found in quiet binary dances, or even in the slow, graceful choreography of cosmic mergers. Imagine two dancers, each moving with immense power and grace. They do not crash into each other in a chaotic mess. Instead, they spiral closer and closer, their movements becoming more and more intricate, their rhythm becoming faster and faster. This is the truth of binary black hole systems. They are a kind of cosmic couple, two immense masses orbiting each other in a slow, patient waltz that can take millions or even billions of years to complete. Their dance is governed by the laws of gravity, and as they spiral closer, they send out those gentle ripples we spoke of before. The gravitational waves, a silent song that tells the universe of their impending union. This is a beautiful and strange truth. The black hole, in its quiet existence, is not alone. Many, if not most of them, are thought to exist in these binary systems. It's a testament to the idea that even in the most remote and mysterious parts of the universe, there is a kind of companionship, a quiet, shared journey. The two black holes orbit a common center of mass, their dance becoming more and more intimate, their final union a quiet, deliberate embrace. The final moments of their merger are not a violent explosion, but a seamless joining, a quiet surrender of 2-to-1. Did you know that the gravitational waves from these binary black hole mergers are the only way we can see them? This is a strange but true fact of the universe. Because black holes are invisible, a binary system of two of them would emit no light, no X-rays, no gamma rays. They would be entirely silent, entirely unseen, if not for the ripples in space-time they create, as they orbit and eventually merge. The detection of these waves by LIGO was not just a scientific breakthrough. It was the first time humanity had ever truly heard a black hole. The first time we had seen the invisible, felt the unfelt. This raises a fascinating and unsolved question. What happens to the information of the two original black holes when they merge? Is it simply combined into the new, single entity? Or is there a quiet loss, a gentle forgetting of their individual histories? The truth is, we don't really know for sure. The physics of black hole mergers is a new field of study, a frontier of human knowledge where the universe is quietly asking us to reevaluate our deepest assumptions about the nature of reality. The black hole, in its quiet, patient existence, is a great unifier. It is a testament to the idea that even the most immense and solitary things are in a constant state of flux, in a slow, patient, and beautiful dance with the cosmos. It reminds us that nothing in the universe, not even a black hole, is truly separate from the rest. It is all one great connected tapestry, and the black hole is simply a place where the threads are woven with a quiet, profound grace. It is a place of cosmic connections, a silent link in the great chain of being. We have explored the binary dances and silent mergers of black holes, those quiet cosmic connections that ripple across the universe. But what if the black hole's role is not just to collect and merge matter, but to serve as a kind of cosmic shortcut, a link between distant parts of the universe? This is the fascinating and deeply speculative idea of wormholes, a concept born from the mathematical intricacies of general relativity. Imagine you are on one side of a vast, uncrossable chasm. To get to the other side would take an immense amount of time and effort. But what if there was a secret hidden tunnel that connected the two sides, a shortcut through the very fabric of the landscape itself? A wormhole, in theory, is just that, a tunnel through space-time, a bridge that could connect two distant points in space, or even two different points in time. It is a concept that is beautiful in its simplicity and profound in its implications. The idea of wormholes was first explored by Einstein and his colleague Nathan Rosen, who found a mathematical solution to the equations of general relativity that described a kind of bridge through spacetime. This is known as an Einstein-Rosen bridge. In this model, a black hole at one end would be connected to a white hole at the other, a kind of cosmic exit ramp from which matter and light could burst forth. It is a concept that turns our idea of the black hole on its head, seeing it not as a final destination, but as a kind of cosmic transit hub. Did you know that according to the mathematics, a wormhole could not just connect 2 points in space, but could also connect 2 different points in time? This is a strange but true fact. In theory, if you could travel through a wormhole, you could emerge at a distant point in space and at a different moment in time, a kind of cosmic time machine. This raises a fascinating and perplexing question for physicists. What would happen if you traveled through a wormhole to a time before you entered it? This is the famous grandfather paradox, where you could theoretically travel back in time and prevent your own existence. This is why many physicists believe that wormholes, if they exist at all, would have to be either unstable or protected by some unknown law of physics that prevents such paradoxes. The truth is, we don't really know for sure if wormholes exist. They are a theoretical concept, a beautiful mathematical possibility that has yet to find any evidence in the real world. The universe seems to have a quiet, elegant way of preventing such paradoxes. It is a testament to the idea that the laws of physics are not random, but are woven together with a kind of profound internal logic that ensures the cosmos remains a coherent and consistent place. The black hole, in its quiet, patient existence, is the key to this mystery. If wormholes exist, they must be intimately connected to the black hole's strange and warped geometry. It is a place where the universe's rules are stretched and bent. A place where the most profound and mysterious possibilities lie hidden. The black hole is not just a cosmic vacuum cleaner. It is a profound and unmoving mystery, a riddle whispered to us by the universe itself. It is a reminder that the quietest places in the cosmos often hold the most incredible and unexpected secrets. We have contemplated the possibility of wormholes, those hypothetical cosmic connections that might link black holes to distant corners of the universe. But now, let us return to the black hole's most profound and certain quality: its age. A black hole, in its quiet existence, is a true ancient. It is a patient observer, a silent watcher that has seen the universe evolve from a young, turbulent place to the sprawling cosmic landscape we know today. Imagine you are sitting in a quiet, still room, and outside your window, you can see the entire history of the universe unfolding in fast forward. You would see galaxies forming from clouds of gas and dust, stars bursting into brilliant light and then fading into silent darkness, and entire cosmic structures rising and falling. A black hole is that quiet watcher. It is a monument to cosmic time, an entity that is so ancient, so patient, that it perceives a billion years as a fleeting moment. The age of a black hole is directly related to its mass. The more massive a black hole is, the slower it evaporates through Hawking radiation. This is a strange but true fact of the universe. A stellar mass black hole, one formed from the collapse of a star, would take an unimaginably long time to evaporate, far longer than the current age of the universe, which is roughly 13.8 billion years old. A supermassive black hole at the center of a galaxy, on the other hand, would take even longer, perhaps quadrillions of years, or even longer, to completely disappear. This raises a fascinating and beautiful philosophical question. If the universe is destined to continue expanding and cooling forever, and if all the stars will eventually burn out, then what will be left? In the far, far future, the universe will become a dark, silent place. The last stars will have winked out, and the last of the cosmic dust will have settled. What will be left? Only the black holes, those quiet, patient watchers. They will be the last living things, so to speak. The final remnants of a universe that was once filled with light and energy. They are the cosmic relics, the final unmoving monuments to a long-forgotten age. Did you know that the largest known black hole is a supermassive giant with a mass of about 40 billion suns? It resides at the heart of the galaxy Holmberg 15A. It is a true behemoth, a silent ancient ruler that has watched its galaxy mature for eons. It is a testament to the quiet, unimaginable power that can be contained in a single point. This raises another interesting question. Is there a limit to how large a black hole can get? We don't really know for sure. Is there a point where its gravity becomes so immense that it becomes something else entirely? The truth is, we are still just beginning to understand these immense patient watchers. The black hole's immense age and patient existence are a kind of cosmic comfort. It reminds us that even in a universe of constant change and motion, there is a place of profound stillness. It is a place that has seen the birth and death of countless stars, the rise and fall of entire galaxies, and the slow, inexorable march of cosmic time. It is a living memory of the universe, a quiet, unmoving chronicle of everything that has ever been. It is a testament to the idea that some things are so powerful and so ancient that they don't need to move or change to make their presence felt. They are simply there, a quiet, eternal witness to the great cosmic play. We have traveled a long, tranquil journey through the quiet lives of black holes, from the gentle embrace of their gravity to the patient observations of their immense age. We have seen them not as monsters, but as sleeping giants, cosmic anchors, and silent watchers. But what is the final chapter in their story? In a universe of constant change and motion, even the most patient and stable things must eventually come to a peaceful end. This is the ultimate fate of all black holes, a quiet, inexorable return to the void from which they came. In the far, far future, the universe will be a very different place. The last stars will have burned out, their faint embers long since gone cold. The last cosmic dust will have settled, and the universe will be a cold, dark, and silent sea. All that will be left are the black holes, those patient final relics. But even they are not immortal. We spoke of Hawking radiation, that faint, almost imperceptible whisper from the black hole that slowly, quietly, drains it of its mass. This is the final act, the slow, peaceful evaporation of the universe's ultimate secret keepers. Imagine a block of ice sitting in a perfectly still, empty room. It doesn't melt in a violent, dramatic rush. Instead, it sublimates, the water molecules quietly and individually leaving the surface, a slow, patient transition from solid to gas. The black hole's evaporation is much the same. It is not a dramatic, fiery explosion, but a gentle, steady, and unhurried fading. The mass of the black hole, which was once the mass of countless stars, is quietly converted into a trickle of thermal radiation, a final, soft breath that fades into the endless cosmic night. This process is so incredibly slow that it is almost incomprehensible to the human mind. The largest supermassive black holes will take quadrillions of years to fully evaporate. It is a process that will take place long, long after the last of the stars have died, long after the last remnants of our own civilization have been forgotten, and long after the universe we know today is nothing more than a faint, distant memory. It is a testament to the patient, unhurried nature of the universe, that even its most powerful creations are designed for a quiet, eventual return to stillness. Did you know that the rate of Hawking radiation is so low that a black hole formed from the collapse of a star would have a temperature that is just a fraction of a Kelvin above absolute zero? This is a strange but true fact of the universe. It is a thing of such immense power, and yet it is colder and more silent than the deepest parts of space. This raises a fascinating and profound question. What happens to the singularity at the very end? Does it simply vanish? Or is it the quiet seed for a new kind of existence? A new beginning after the final end? The truth is, we don't really know for sure. It is one of the final mysteries of the universe, a question that connects the beginning and the end in a single, unmoving point. The black hole's final act is not a violent explosion, but a peaceful surrender. It is a long, slow goodbye to the universe it has watched for so long. It is a final, quiet dissolution, a graceful transition from a state of being to a state of not being. It is a quiet reminder that all things, no matter how immense or powerful, must eventually return to the gentle, unmoving sea from which they came. It is the end of the story, but it is an end filled not with sadness, but with a profound and tranquil beauty. And so, our journey ends. We have traveled to the quiet heart of the cosmos and found not a monster, but a sleeping giant, a patient observer, a keeper of cosmic secrets. We have seen how gravity can be a gentle cradle, how time can be a slow, quiet river, and how even the most immense forces in the universe can act with a kind of profound and beautiful stillness. The black hole is not a destination of fear, but a destination of peace. It is the universe's ultimate sigh of relief, the final quiet home for everything that was once a part of the light. I'd like to gently ask one last time, where is the place you're staying now? The time in that place, at this very moment, how is it flowing? Perhaps you are in a different city, a different country, or a different time zone. But wherever you are, and whenever you are, remember that you are a part of this great cosmic story. The same quiet laws that govern the black holes are also the laws that govern the gentle breath of your own life. You are made of stardust, and you are a part of this patient, beautiful universe. So, as you slowly drift to sleep, know that you are in a quiet, safe, and beautiful place. There is no need to worry, no need to rush. The universe, in its own way, is just as patient and tranquil as the sleeping giants we have explored. Take a moment now to breathe deeply and slowly. Feel the gentle weight of your own body, the quiet rhythm of your own heart, and let your mind drift like a leaf on a slow, peaceful current. You are a part of a much larger, much quieter story. Sleep well, my companion, wherever and whenever you are. Sweet dreams.